We will now talk about the capacity of point-to-point MIMO channels, where we have multiple antennas at both the transmitter and the receiver, while in the previous video we were only having multiple antennas at one of these 2 points. So we have K transmit antennas and M receive antennas. That means that between each transmit antenna and receive antenna we have a scalar value that is describing the channel. GMK from the K transmit antenna to the mth receive antenna. In total we have M times K channel responses to describe this channel, and it's convenient to put them into a matrix capital G, where the row is describing which receive antenna we are considering and the column is describing what transmit antenna we are considering. Let's now look at the received signal at the nth antenna. It's a summation of the signals coming from all of the K transmit antenna. XK is what we transmit from antenna K. We multiply it with GMK, and then we add the noise NM. And we do this for all of the different receive antennas. And then we could put it all into a matrix form. So we have a received vector Y, which is m-dimensional. We multiply the channel matrix G with a vector X that contains the transmitted signal X1 to XK. And then we add a vector N that contains the noise from all of these receive antennas. Here is a block diagram showing the channel. We are transmitting the signal X, it's get multiplied with the channel matrix G, we add a noise vector N to get the received signal Y. So Y is equal to G times X plus N. The total transmit power is still equal to Q in energy per symbol, so that means that the square norm of X should be equal to Q. And each of the elements in the noise vector N have a noise power spectral density of N naught. Our goal is to find the capacity of this MIMO channel, and then we need to select how the transmitter and the receiver is working. In general, we can let the transmitter select the vector X as X tilde, which contains the information, times a matrix V. And at the receiver side, we can let Y be multiplied with the matrix U Hermitian to get Y tilde, which should be very similar to X tilde. And how can we select V and U? Well, there is a trick that we can do, and that is by selecting V and U as being singular vectors of the matrix G. That is like an eigenvalue decomposition, but more general for cases when the G can be a rectangular matrix. By selecting V as the right singular vectors of G and U as being the left singular vectors of G, we can parallelize the channels like this. Capital S is the rank of the matrix, which is smaller than the minimum of M and K. By using this trick, we are turning the point-to-point MIMO channel into capital S parallel SISU channels. So the first one is where we're transmitting X1 tilde. It's multiplied with the channel response S1, which is the first singular value. Then we add a rotated version of the noise, N1 tilde, to get Y1 tilde. And it goes on like this for all of the parallel channels. Here is a geometrical interpretation of this singular value decomposition. We have 3 transmit antennas and 3 receive antennas. And capital S is equal to 3, so that means that we are dividing the channel into 3 parallel subchannels, the red, blue, and green one. For each one of them, we have a precoding vector, which is selected from the matrix V. So each of the columns of V is one of the 3 precoding vectors. And at the receiver side, we have a combining vector, which is taken as one of the columns of U. So we have the red, blue, and green one. Then the strength of each subchannel is given by the singular value. So S1 is the strongest one, then comes S2, and then finally S3. In this example, the blue path is a direct path between transmitter and the receiver, while the red path is going via one scattering object and the green path is going via another scattering object. And the singular value decomposition finds a way of decomposing the channel into parallel subchannels that are totally independent of each other. For each of these parallel channels, we know the capacity if we operate it individually. So for the kth subchannel, we are getting log 2 of 1 plus qk sk square divided by n naught. And now we have capital S parallel channels, so we sum it up. And what remains is to figure out how we should take our total transmit power Q and divide it between the S parallel channels. So we have Q1 to Q capital S, where we need to make sure that the sum of them is equal to Q. The optimal power allocation is known as waterfilling, and here is the formula for that. You find it with some optimization tricks. So for subchannel K, QK is equal to either 0 or mu minus N0 divided by SK squared. So SK squared divided by N0 is something that shows up in the SNR of that subchannel. And you take the maximum of these ones, so the power can never be smaller than 0. But since we are subtracting something, it can happen that the first term here is negative, and then you use 0 power. We call it waterfilling because we can view it as pouring water into a pool which has an uneven bottom, describing each of the subchannels here. And for the case one, we have N0 divided by SK squared. That's what we're subtracting, and that is then the height of the bottom at that point. And then we are pouring water into it. And first, when we have just a little water, it will go to the strongest channel, channel 1 here, where we're dividing with S1, which is the largest value. And then when we add more and more water into it, we are reaching up to the second channel, the third channel, and maybe we will eventually have power on all of these channels. So at low SNR, or when we have a little power, we will maybe only use one subchannel, the best one. And when we're highest now, we will put water onto all of these subchannels and approximately give them the same amount of power. When I talked about the Simon-Meisner capacities in the previous video, I concluded that the main benefit is the beamforming gain. The SNR grows proportional to number of antennas, which means a lot at low SNR, but at high SNR, since the capacity is log 1 plus SNR, we are only getting a logarithmic growth with the number of antennas, which is rather slow. When we have multiple antennas at both the transmitter and the receiver, we get also what we call a multiplexing gain, which is a much larger thing. So we have the summation over the number of subchannels, and that was the minimum of the number of transmit and receive antennas in general. And if we now increase the number of transmit and receive antennas together, we can increase the capacity linearly with the number of antennas. And that goes much faster than having a logarithmic gain. So that is the main benefit of point-to-point MIMO channels. The multiplexing gain, the capacity at highest now is proportional to the minimum of the number of transmit and receive antennas.